Benjamin Franklin once said, "The bitterness of poor quality remains long after the sweetness of low price is forgotten." The fact is, quality matters. Join us as we make quality fun, interesting, and accessible to companies of all levels. Quality Matters is a must-listen for all things quality. Listen in, ask questions, and get back to doing what matters most. Quality Matters, brought to you by Texas Quality Assurance, where quality management gets simplified.
All right, welcome back to the Quality Matters podcast. I'm Kyle Chambers with Texas Quality Assurance, and as I have been promising, and I know you're probably like, Kyle, we're getting tired of hearing it. You're going to get more regular with the podcast, but we really are. We finally have a plan and a strategy that I think is going to be sustainable for us. So with that, we're going to be changing it up a little bit. We're going to be having as a regular guest on the podcast, kind of co-host, really, I think it's going to be, is Caleb Adcock. He's our software manager for us here at Texas Quality Assurance. So we'll be introducing him in just a minute. And our guest today is Robert Mimms. So it's been a while since he's been on the podcast, but Robert's fantastic. Just so much wealth of knowledge when it comes to metrology. So we're going to be having a real fun conversation about that today. So Robert is a metrology specialist with Prosper Machine Tools. Forgive me, you can see me looking at my notes. I have to write it down. Memory's terrible. And that's probably why we built quality management software, because you can't remember anything. So with all of that, let me go ahead and get the team brought in here. So Caleb, say hello to the world.
Hey, hello, everyone.
All right. And Robert, good to talk to you.
Hello.
Again. Hey,
yeah,
we got you on a different order.
Back.
Caleb, I'm covering your face with our logo. There you go.
All right.
Up there in the corner.
I mean, yeah.
Oh, all right. So, Robert, not everyone knows what metrology is. This was a term like I'd never heard of, until about 15 years ago. So, this is what's this kind of weird, geeky sounding word, and why did any of us care about it?
So metrology is the science of measurement. I'm specifically focused on dimensional metrology, so the science of distance measurement. Now,
Okay.
I don't have any fancy engineering or physics degrees, which is what a lot of metrologists have. But I have 15 years of experience in the industry, and I make it my hobby to study this absolutely deep and fascinating subject.
And I've been never hid my feelings on it. I'm not saying college is useless. I'm saying it's just not, worthwhile for most of us. And so if you can find a way to learn and do what you need to do without it, then by all means go for it. Not that I don't believe in education, just, you get the idea. Well, degree doesn't mean much to me.
It's like an education on demand.
Yes.
Yeah. It's amazing.
I've never met anyone that set out to get into quality, and it's just kind of a weird world. And you're in that parallel path to the quality world.
Yeah, and that's kind of how you and I connected many, many years ago now. I mean, we've known each other for a long time.
This is weird. I remember all this was like brand new, and still some days I'm like, man, this still feels like new. And it's like, it's been a while.
Yeah, because I don't. A lot of small companies, probably a lot of the ones you work with, Kyle, focus a lot on like quality. Their quality guy is also in charge of all their calibrations. They're in charge of all of that as well. And I think you and I both see them very much as different entities, the quality and the metrology side of it. Yes. So like if we worked at the same company, you'd be the quality manager and I'd be the lab manager or somebody in that sort of roles.
That's it. They're separate worlds. Yeah,
they are different skill sets too.
Oh yeah. I mean, look, if you're at a, say you're a small machine shop, you guys got a handful of calipers. All right. Not such a big deal. But the moment you've got a lab and you're starting to do a lot of the work internally, like I remember at one point we decided we wanted to do all of our spot checks in-house instead of sending everything out. And management was like, oh, well, that's simple. Just get a set of standards and we're good. I'm like, no.
Math doesn't work like that, unfortunately. But there's a difference, and I think one of the focuses of the metrology field, and in dimensional metrology especially, is measuring a size is a moving target.
Yeah.
It drops by a degree in temperature, or it you're in a different atmosphere, or the tool is calibrated on a mountain and you're in a valley, you know.
Yeah.
Everything, vibrations of the
Matters.
machines around you, the amount of airflow, all affects the size of something. So what
Yep.
I call myself a metrology specialist instead of, you know, a calibration or a technician, because for me it's about chasing that number. It's like how can we build the best process so that we get as close to the correct number as possible every time.
Yeah. And now I can hear, so many people in the background mind saying, well, if you get a repeatable result, then that means it's good. We got a repeatable result. But what you're saying is that's not quite the case.
Oh, 100% not. I mean, there's, it's kind of like people who think resolution and accuracy are the same thing. Just because something can do something or says it's the same, I mean, that number could still be off by your entire tolerance band. And it could be repeatable within your tolerance band.
Yeah.
I mean,
so tell me how accurate this would be or not, because I've debated using this description for some of my clients before when we're trying to explain like when they really need to start paying more attention to calibrations, and especially when it's like a large production line where the maintenance and preventative actions ain't good. That's a whole other conversation. But would this be a good analogy? So let's say that you're a good marksman and you're shooting down range, right? So you never are inaccurate by more than 2 inches. You're always within 2 inches, but you're generally spread out within 2 inches versus you're hitting it bullseye in every 10th one your way out. That's where we're kind of talking about accuracy versus resolution, and like how on target are you? Like how much of a spread do you have there? How much does that matter?
Yeah. In some ways, I think you're heading down the right path with that. I think that if the best way that I would just use your analogy and build upon it would be the resolution of the machine is the number of rings on your target. And then the accuracy is how close together how close to the nominal, to the center, those are.
Even if they're off, they're consistently off in the same location.
Yeah, so that's repeatability.
Yep.
Is they're all together. And accuracy is how close are they to zero.
Okay.
Or to that bullseye.
Okay.
And if you think about it like that, it's pretty straightforward. I mean, at least in my head, although I'm the same guy who can reach behind me and grab at least 4 textbooks on metrology. So
I think this is kind of a good way to go with it, though, but anyway, that's kind of for my own benefit, because I'm trying to find some ways to explain this in situations where the company's just on that cusp of, do we do something better internally or do we keep outsourcing this?
That I mean, that's a whole podcast. When to decide, how to decide, who to go to.
But here's the segue I want to make with it, because all of this, again, if folks listening to it, you're like, what's it matter? Why do we need to be that tight on the tolerance? Like, how tight can we really go with this stuff? Like, how far down this rabbit trail do we go with dimensions, and when and why does it matter?
So I actually have a input there. So, I started out as a welder, and then I became an inspector. And part of my inspection training was I was working in a machine shop, and I just kind of got thrown into that. They say, here's a pair of calipers, here's an old guy, like learn from this guy. And
it's a good way.
He'll teach you all about it. So, he swears by this 1930s lathe and press and won't even use it anyway. So you start dealing with that small of dimensions, you're talking about 1,000th of an inch or whatever, 5,000ths of an inch. Like you start at first, you're like, I can't even fathom that. But then as you start looking at like a 16th of an inch, and you're like, wait a second, I can actually kind of start seeing when something's a 16th off, because I've been looking at thousands, and so I'm like, as an inspector, you look at blueprints and you see, okay, you got a 3-inch dimension between 2 holes, right? And so you're like, you got a 5,000 tolerance, which is pretty much not needed in most industries, or the engineer wants that. But so as an inspector, you're getting all caught up in that. But then in the actual use of the tool, it's like it's either going to fit or it's not going to fit what it's being made for. And so that's what, when Kyle was like, well, when is it important? When is it? And like, when you're removed from the process, when you're removed from the tool itself and what it's being used for, all you have is that blueprint. And so like, yeah, I thought that was a good, like, okay, well, when is it important? Like, as long as it fits what the customer wants, it doesn't matter. But and I think you're talking a little bit more about standards and.
Yeah. No, I think first of all, what you just said was awesome. I mean, those are the types of thought processes that. How accurate do we need to be? And the answer is, in my personal professional opinion, if you are measuring something, your tool should be at least 4 times more accurate. That would be mil spec. So military specifications state that your tool should be 4 times more accurate than the accuracy of the measurement you're supposed to take. That's what we call a 4-to-1 ratio. Now, sometimes a 2-to-1 ratio is okay. In super extreme, hey, we know what we're doing, we are in a controlled environment. I've even seen 1-to-1 used on very high-end calibrations because there's nothing more accurate than the tool that you're calibrating. So you have to calibrate it to something equally as accurate.
So when you say 4-to-1, do you mean like, okay, let's say you're working with a machine that obviously has a little bit of wobble or vibration, and they're expecting, like, you're saying that your measurement tool should be more accurate than the machine itself, or what did you?
No, then on the drawing, there's always a call out for an accuracy. So let's say I pull out a
Okay,
caliper,
yeah,
which I can do here in a sec, and I'm measuring a bore or a shaft. So I take it and I'm measuring a shaft. I want that caliper to be 4 times more accurate than the call out on the print for that shaft.
Okay.
So if it calls out a thou, I want something that has, half tenth, or I mean, like half a thou, quarter of a thou resolution.
And then all those uncertainties and issues, those can mostly be discounted at that point.
Exactly, and that's what you're doing is because every measurement, no matter where you're at in the scale, has an uncertainty value to it.
Yep.
So if you go to Mitutoyo and you ask them to measure something on their leg X that they have in a super controlled lab, only like they don't measure anything when a second person is in the room. The door's not allowed to be open. It actually blocks while it's measuring. It's the most insane machine CMM that I have ever seen. And I do make the argument that they do make the most accurate CMM, but every CMM manufacturer argues that.
You're a Mitutoyo guy, at least in that aspect, huh?
Well, I mean, it does help that. So Prosper Machine Tool, where I work, we basically only carry 2 metrology lines, and that's we're a full line distributor for OGP, which makes vision system based optical comparators. So basically an optical comparator that uses a video camera instead of a touch probe, a vision system, sorry, is a CMM that uses a camera instead of a touch probe. And then you have Michitoyo, who makes, in my opinion, one of the best CMMs on the market. And so, that's all I work with for the most part anymore. We don't really deal with hand tools. I only deal with the really high-end super accurate machines these days.
Okay, that makes sense. Well, so tell me, like, you say super accurate, like what's super accurate? So I guess for context, Caleb, you were weld inspector. What type of tolerances did you see that anyone cared about? What was the high end that you had to deal with?
Oh, I mean, it depends. Structural, that gets a little and then again, it's an opinion. You see what's on this print, but then you get to application. You got standards and stuff that say it's got to be. But I mean, in general, like in manufacturing and large scale manufacturing, 16th, something like that. Some people try and say a 32nd of an inch, and you're like, but. And then you get into the machining world and you start getting like, okay, these 2 holes have to be this far apart or else what it's being connected to is not going to work. Then you start getting into 5,000s, which I think a 16th is 0.006. So a little bit smaller. Yeah. So.
Yeah. So I work in 2 different systems. Obviously, I work in SEA and I work in metric. Most of the math, really the root of most of the math is all in metric. So and honestly, everything is mastered in metric. So even if you go out and you buy yourself a set of gauge blocks that are inch gauge blocks, somewhere in its traceability, it switches to metric. And that just has to do with the fact that the SI, which is what all of our measurements are based on, is a metric system. So the first thing I like to bring up before we get into accuracies and diving down that rabbit hole is kind of when I recommend using metric and when I recommend using imperial or SEA. So that's kind of where I generally would like to start that conversation.
I think for practical, I mean, I don't know. There's no clear answer here, but I think anything practical, once we get past what we can do on a ruler, it's all metric.
That's exactly actually one of the way that I word it. If you can't measure it on a tape measure, I do it in metric. But I have a question for you, and I don't know if I've ever actually had this conversation with you, Kyle. But I'm going to ask it to Caleb in case I have. Caleb, why would you? What is the primary difference in measuring between the metric system and the imperial system? And it's not the size of the section.
I mean, it's I would say my guess would be like the base 10, if that's the right word for it. Everything's in tenths rather than 12 inches versus everything. People would say that our system is kind of jacked because it's like 12 inches equals a foot, 36 inches equals a yard. So I would say base 10 is the biggest.
So there's
that's the right word.
Beautiful piece and you're leading into it perfectly. You had mentioned base 12 versus base 10. Do you know why base 12 when in the founding of the United States, although I have stories about this too, but when we originally decided to go with the imperial system over the metric system, why we would go for a base 12 instead of a base 10 system?
As a guess, it was either a pride thing or it was a comparative thing of something common in the.
Oh, I do know that this is a cool story. Yes, but no, go. I remember this. Yes, I was trying to figure out where to go.
You talking about the ship sinking story? Yes. I can tell that story too. That's not what I'm talking about. I tell that story all the time. It's one of my favorites. Okay, so if you take a hole, no matter what that hole is, okay, and I fold it in half, I have 0.5.
Mm-hmm.
Everybody agrees with that. But if I fold it into thirds, I have 0.3333333333333.
Right.
So the difference between base 12 and base 10 is the ability to do fractions in it.
Yep.
So 10 is only divisible by 1, 2, 5, and 10 to make a whole number. But 12 is divisible by 1, 2, 3, 4, 6, and 12. Yeah. So because of that, we get an amazingly huge variety of fractions that we can work with. So
it sucks when you do real world math.
Yeah. when you're trying to take that and turn it into something else. I used to keep up on my wall, and I don't have it in my new office, but I used to keep up on my wall a fractional equivalency chart. Mm-hmm. I'm doing everything in decimals, even in the imperial system, and it's just awful. Like, what fraction drill bit is that? On and so forth.
Do you know where like the base 12? Because I just find this stuff fascinating. Like the whole base 12 system. Do you know where the origins of it even come from?
I do, but you're more than welcome to say it.
It's ancient Sumerian and Babylonian cultures. Is because everything was base 12. You could do all of the math on your hand. So each digit, so you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so you've got your digits there. And so you can do a lot of complex math just on your hands. And so that's why our clocks and everything is 360. And so it just stuck because it's a numbering system that I guess biologically works with us. It just doesn't work with math.
Yeah. So I think we've established that the imperial system is better.
So
honestly, in this range, it is better.
Yeah.
If I can measure it with a ruler, it's better.
It gets me when somebody's like, "That's 179 centimeters." I'm like, "What is that?" Like that's 7 feet. Like
Yeah.
7 feet is more. I don't even know if that math
Yeah.
adds up, but it's like 6 feet 4 inches is a lot more fathomable than 130 centimeters.
Okay, so this is not
that's your
anything
training,
technical,
though.
but this is just
Mhm.
like a weird thing. It's like I can't perceive. It doesn't matter how hard I try. I cannot perceive the world in centimeters and meters and kilometers. You tell me feet and miles, I feel it. I sense it. I know how far it is. You tell me kilometers, and I'm like, I know the math. I just
Yeah.
can't intuitively grasp it. It's just so weird how that works.
Yeah, and honestly, that has to do with your upbringing, though. That has a lot less to do. So I was really blessed. I deal with kilometers very rarely. I deal with very small numbers more than anything over a millimeter is pretty much outside of what I have to actually do. But I also grew up kind of split. I spent from up to first grade in the U.S. and then I moved to Australia for 9 years or something like that.
Okay. Yeah.
So
Okay.
a lot of those formative years were in metric, and then come back and did high school in Texas. So where, I'm like,
You're ambidextrous there.
yeah, I guess the big numbers still confuse me, and honestly, I love small numbers in metric. They make so much more sense to me, which actually is
How small does it
interesting.
go?
How it's very small. The funny thing is that the smallest number most of us will ever hear outside of the metrology field is a micron.
Mhm.
But just so you're aware, a micron is 1,000th of a millimeter, but 1,000th of a micron is called a nanometer. And there are machines that exist now that have accuracies measured in nanometers because they're like 50 nanometers. But that's even hard to think about in your mind. And when you get to machines that are technically this accurate, so a great example, I'm actually looking at. I pulled this up because I've seen this machine in person.
Let me throw it up there.
But the Legic series by Metrology, I told you they make one of the most accurate CMMs in the world. If you actually look at the technical documents for this, it actually doesn't give you an accuracy. It only tells you resolution. Because when we hit machines that are this accurate, if you have this in an enclosed room with an AC that isn't exactly right, you're tripling and quadrupling the actual tolerance you can pull out of the machine.
Oh my
as opposed, think about I've been in the room where they hold the machine they use to check scales and to check like glass scales. They also use it to check gauge blocks with one of these CMMs. And what I can tell you is when you walk into that room and you can see the DRO, when you open the door, you watch the numbers jump.
Oh, wow.
That isn't including like your body heat in the room, heating it up by 1/10 of a degree. And these machines are sensing that. So when we get to this type of accuracy, this micron accuracy, it's past most people's comprehension of what a measurement is. And even the more you get into the math, it kind of feels like guesswork because you're like, I mean, plus or minus a micron, like in your head.
So
it's. Go ahead.
Where would this type of accuracy be required? I mean, I understand, let's say you're building calibration blocks, that kind of thing, that are going to be testing calipers and stuff, but what are some other applications where that type of tolerance would be?
In the electrical field, we get a lot more super accurate. You're measuring the spacing between
like
conductors.
Yeah.
But
that makes
stuff
sense.
like that. They usually use a microscope, a visual system. Thousands of brands out there. OGP is one of them. They make an amazing machine, by the way.
It's been a minute, but I can remember, once you start looking at threads in a machine shop, and I think I think it's called an optical comparator. Is that like, it's been a decade? But you start measuring threads and spacing and stuff like that, and it gets to a point where you do have to. When we used to take molds, and then I'm sure it kind of baffled me how they did this, because you would think you'd lose some accuracy here, but you take a mold and then you put that on the comparator, and then you're able to like blow that up, so you're actually able to measure to scale. And I was like,
Yeah.
that blew my mind. I never even thought, okay, that's how especially with threading.
Yeah.
If you put out hundreds tools and the threading's wrong because you couldn't measure it right, or your jig was wrong or something like that, that's a big deal. That's a lot of money.
Yeah.
So it's all. I actually was considering metrology before I decided to go like the full on, like, because
Quality.
nobody ever stops and thinks is like, what is an inch? Who defines what an inch is, or who defines what, like, and I actually had to look it up, and I don't. Yeah, I'm sure you probably could define that better, but it's like how long light takes to travel in a tube, or something like that.
Yeah.
Okay.
So the fascinating thing, before I go too far, is there's only one. I can't think of the name of this. Where basically something defines something, and then that thing defines the first thing.
Yeah.
I don't, like a loop.
It's self-referential.
Yeah, and quality, in the quality world, in the calibration world, those are avoided at all cost.
Yeah.
But there's one place that is considered a constant.
Hang on.
And that is the speed of light is equal to just under 300 million. Hold on. Let's make sure. I think it's 300 million meters per second. Yeah.
You can't avoid it.
That's the speed that it is. And by the way, the original speed was obviously 300 million meters per second, and then we got either more accurate tools, or something happened with our calibration system and we no longer read it as 300. I've never figured out why this number, but then the meter is actually defined as 1/299, so on and so forth, of the speed of light, because we use light to measure. So it's the one, and that's the SI.
Yeah.
It's the one time that it's okay, because they're both constants, right? We know time. We measure that with the decay of a cesium atom.
What if that changes? I don't know if that's physically possible, but what if the speed of light changes, or what if the decay changes because of?
Actually, I love this question because it'll take us down a completely different rabbit hole. But if the speed of light ever changed, we could never prove it.
Yep.
Because the only way to measure the speed of light is from here to there and back again.
Mm-hmm.
And it's the same argument that if the speed of light is directional, meaning you see in one direction easier than you see in another, you can't ever prove it, because you have to go both ways to know that it happened.
Yep.
So, and whether it's through an electrical line or through a fiber optic cable or whatever it is, that time is what,
All right.
We can't prove it's different.
Do like a little bonus geek out episode on this, but I'm gonna have to, as much as I want to go down, I gotta get it. Oh man, because this is the stuff that I find really fascinating too. Well, I find I'm just a geek about anything. I was talking to my wife the other day. I was like,
"How do we get along?"
She's like, "Kyle, is there anything you don't find fascinating?" It's like, other than your TV shows, not really.
Yeah, I was going to say Real Housewives.
Reality television.
That was not the right answer.
Oh, it's all right. My partner does the same thing. She watches TV shows that I am like, I'm gonna go build something, or do something like that. Well, so I pulled that Micron thing back up.
Yeah, I'm gonna pull that up.
You want me to talk about this for a second?
This is pretty cool, because this gives some context, and like a lot of machine shops really have to worry about this stuff. Like I remember when I was at the turbine shop, we'd go down to a 10,000th of an inch very regularly. But I'll be honest with you, I never quite grasped what is that. I just knew that number we had to hit.
So since we're working in metric here, this is a great metric designation, a great way to think about the size of a micron. So just for the sake of, for you imperial people, a micron is 40 millionths, 39 point something millionths of an inch.
Oh, fun.
Is 1 micron.
Okay.
Also 1,000th of a millimeter. So 0.001, just so that in your head you're thinking. So 180 microns would be 0.180 millimeters.
Okay.
Just so that we're thinking about decimal places and how this is written. So 1 micron is a number that people throw around a lot. Oh, it's out by a micron. Oh, what is a micron? Well, the smallest mold spores that you can find are a micron,
Oh, wow.
which is completely, you can't see them, you can't smell them. They're floating particles in the air. It's what causes your allergies to go crazy. But that's a micron, and they're all around you, and you're not seeing them. It's not visible. Now, when we get to bacteria at 70 microns, 70 microns is actually past the visible spectrum. So if you were to see something that was 70 microns, with your eyes, you would see what appears to be like literally the most minute thing your eyes can pick out, like a change in color. It's not really visible at 40 microns, but it's
right. That would be the highest we could possibly see.
That you could possibly see is 40 microns.
Yeah.
Well, so the thickness,
white speck.
the thickness of the paper is 70. We can see the thickness of the paper.
Yeah.
I mean, at least I think I can. So
you
if
can
that
see it.
if that bacteria were as long as a piece of paper, then we'd see it. But it's still thin as the. Okay, so that's what I'm like. Where does the visual stop? Because I can see the thickness of a paper. What it is? So would it be about like 70 or 65 microns or?
Yeah, you're gonna find 40 microns is considered we can see this. How big does it have to be? I mean, honestly, I'm blind as a bat. What I can see and what Kyle can see are probably completely different. Even same with you, Caleb. Your prescription is probably different. With a nice little zoom reticle, I can see a lot more. Even just a 2 times reticle changes a lot.
Okay.
The one thing that I like to point out here that really hit home for me when I was trying to study this, though, is the red blood cell. So, you get a cut on your arm and you're bleeding, you feel like that is liquid. But that liquid has in it these 7 micron blood cells. I'm sorry, I keep looking at my notes on the screen.
Yeah.
And we can't imagine how small our red blood cells are, but we measure those in microns. So every once in a while, I'll find a customer who's looking to do, like half of a 10,000th of an inch as their accuracy. Yeah, that's 500. Sorry, Caleb, I just saw your face. I'm pretty sure if my SEA is correct, it's 500 micro inches or 500 millionths of an inch.
Okay.
Which is about 10 microns, right? Maybe 12 microns.
All right.
So thinking microns now.
I would encourage you. I try not to do this, John, but I would encourage you to go check out the YouTube channel on this because it's a really cool graphic up here. Maybe we can put a link to it in the show notes too.
Yeah.
Go through the difference here. So what you're talking about, the accuracy they want. We've got like the references here. So thickness of the paper, human hair, a blood cell, bacteria, mold spore. What multiple of these are they looking for accuracy to?
Yeah, so I pulled this up just to give us a visual thought in our head of what a micron is. But, generally when you're starting to talk about microns, and the danger zone that you really cross into is after about, if you have something closer than a 20 micron accuracy. So something smaller than that little tiny hair that curled up and you can't even really see it. It's that invisible thing in your eye. Yeah. That type of smallness, once you start getting smaller than that, we start entering into danger territory where we're starting to get very, very, very expensive to measure something.
Makes sense.
So,
you're going to have to control all of the conditions, including the vibration of the floor.
Yeah. So a turn check, for example, which is an OGP laser system used for measuring outside diameters of cylindrical parts. I know that was a lot of words, but if you're in the industry, you know what I said. If you're not in the industry, it measures things with a laser. I don't mean that in a rude way, but it's like I could spend 3 hours.
We only got so much time.
Yeah. That has an accuracy without any. It has some temp comp and stuff in it, but without any external sources on it. It has an accuracy of about 7 microns, maybe a little bit tighter than that.
Okay. So what for real? I say real for kind of modern everyday things that folks run into, what type products, I guess, and you may not even be able to answer this question, maybe an unfair question, but like what type of products do people interact with on a daily basis that needs this level of detail?
Oh, great example is your cell phone.
Oh,
The inside
okay.
of your cell phone is full of very accurate measurements from the way the circuit board is put together. As far as everything, I mean, there's so many things we take for granted. The car engines, like the spacing between the cylinder and the piston, you know, stuff like that are very accurately measured at the factory because they have to be measured in a way that will last forever.
Right.
So they have to start in a good place. Great example, medical. All sorts of medical stuff has crazy tolerances. I worked with a customer that trying to decide if there's anything in what I was about to say that I'm not allowed to say. That makes
fun,
machines for sewing internal organs.
Oh, fun.
So it's like a sewing machine.
Yeah.
That
I got you.
It's actually gastrointestinal, so they can put it down your throat. And so it's absolutely the most absurd thing.
Cool.
I worked on it and I was like, what is this thing?
That's
And they
so
kept
cool.
bringing out 3D printed parts that were like, you know, something you could visually see. Well, we're trying to measure this here. And I'd be like, oh, okay, that's easy enough to do. And then they'd bring out the actual part and it's, you know, this
Like, where is it?
My brain is having, you know, oh wait, that was really easy on that one.
Yeah.
But now you're showing the tolerances and because, you know, it is really hard to visualize it if you can't see it. And a lot of these parts that we are measuring to those types of accuracies, watches have a lot of very accurate measurements in them, stuff like that.
Well,
Okay,
even
so
like the needle that you get a shot with, I mean, that's super thin, you know, but the
the wall
you gotta-
thickness on that, how it's cut, all of that stuff is not quite micron accuracy, but you're getting into some pretty tight tolerances there. And the great thing is that this industry is always growing. This industry's always got new products coming out to meet the demand of the new, more accurate manufacturing. And honestly, I think that if you're talking about sizes and you're talking about, you know, the one thing that really matters to, you know, president of a company or to, hey, we're talking about measuring to this accuracy, what do I need to know? And in my head, you know, once you get below 1/10 of an inch or that, you know, 20, even 50 microns, you start getting into an exponential price increase for everything you do.
Yeah.
So, you know, to go from measuring from 4 microns to measuring 2 microns and to have a 4-to-1 or even a 2-to-1 ratio on that, so that you have the room and your uncertainties to make sure that you're on. I mean, you're talking going from hundreds of thousands of dollars to many hundreds of thousands of dollars. Like,
crazy.
It's like difference between $150,000 or $200,000 machine up to, you know, a $700,000 or $800,000 machine.
Makes sense.
So one of the things that as a manufacturer, you know, especially as an inspector and somebody who maybe, you know, there's a lot of times people make stuff, they don't even see it applied. You know, if your parts are compartmentalized. One of the things I learned as I became, you know, as I got a little bit more experience is like, if you see a tolerance on a blueprint, don't be afraid to call the engineer and be like, hey, what do you actually need here? You know, because no, because there's so many times whenever I'd see like 5/1000 of an inch. Yeah, or that was what was on the last print. I used the same template. And then so you're spending hours or a lot of money reaching these tolerances, and you could have called, or, you know, they're getting the part and like, man, these guys are good. Like, we only have 1/8 of an inch and man, everything's perfect. So
everything's perfect.
Yeah. I mean, which is good, but you have to include that in your prices. You know, like if you're hitting those kind of tolerances, you have to account for that. I mean, unless you just got some machine that spits out perfect parts without any maintenance or anything like that, then, you know, but build to what you say you build. I mean, that's all quality is doing what you say you do and what your customer needs. It's like
proving you're building to do is where the fun part is.
Yeah.
I describe to people all the time, like when you're getting 9001 or you're getting 718025, there are certain guidelines you have to follow. And correct me if I'm wrong, Kyle, because this is your area of expertise. But you know, there's guidelines to follow, but at the end of the day, it's do what you say and say what you do.
Mhm.
If you do something, write it down, put it part of the manual so the next guy does the same thing.
That's
It's about
it.
repeatability and traceability in your workflows.
Yeah, I started telling folks it seems to be a little more impactful because I'm always like, look, we need to make sure that this is repeatable. And then, you know, you try to put yourself in there. She's like, well, it is. I do it the same way every time. Repeatable. I'm done. Great.
Can somebody else do it that way? Yeah.
And it's like, no. So what I try to tell them is like, look, they're like, why do I need to document it? Do your future self a favor. 3 weeks from now, if someone comes back to you with an issue on this, you're not going to remember anything with any detail that you did or problems you ran into today. So just document it for your own future self's sake.
Well, and the concept of do what you say and say what you do is like I've been really investing in that. Prosper Machine Tools working on our 17025 right now, so we're in the middle of a whole quality thing. But because of that, like I think about everything I do. I'm the first technician at Prosper who does metrology, and our goal is to have 3 or 4 of us in time. But everything I do, it's about, okay, if I do this way, is this repeatable for the next guy? All the way down to documenting what tools are in my tool bag that I take into a customer every time. If I change something, changing that on my list so that if at any point we go, okay, we're going to hire a guy, I can say, okay, order this backpack, order this. Because I use a tool backpack. I just upgraded from a toolbox. So it's that mentality. And I know we're way off subject right now.
But that's like I don't have it here actually. I took it home. It was different, but it's the same idea. Is when I was safety manager, I had a toolbox in identical supplies in it. I had one at home, I had one in my car, and I had one in my office. And I know that sounds like overkill, but we had facilities in 3 different places, and I never knew where I'd be. And so in that toolbox was all the basic first aid stuff I needed. It was addresses and phone numbers to all of the medical care providers. It had, all of the information in it. I had my accident form. I had my workers' comp forms. I had copies of the insurance for the guys. And I had 3 identical toolboxes that everywhere I might be. And I mean, it sounds like overkill, but like maybe I don't know, maybe it is. Someone's listening to it like, Kyle, you're a little neurotic. And
well, if you have 3 of identical tools, if you have 3 identical medical kits, you're never going to run into a surprise. You're not going to open up the toolkit and be like, crap, this dude needs a thing of whatever cover or whatever, like real quick. I can't find
what kills us. So if you've got a good quality program, you limit the number of surprises, and that makes life enjoyable. We enjoy little happy surprises. We hate putting out fires.
Yeah. Well, I mean, some of us do.
Yeah.
I was gonna say, my job is putting out fires. Hey, Mr. Technician, my machine is down. My whole factory can't work until this is fixed. Come put out this fire. I'm sorry, Mr. Customer. Yeah. Well, like I'm going to a customer tomorrow. They've got an optical comparator down, and I'm driving down to go fix it. So it's the chaos is good.
I mean, like, that is the normal function. I mean, none of us like the unexpected. Something went wrong because I failed to plan for it type problems. And
great example is
you can eliminate, the more we get to enjoy our job. And correct me if I'm wrong, but I kind of like the idea of enjoying my work.
Yeah.
I mean, I spend more time here than I do at home. I really don't want to be miserable.
Yeah. No. Nobody else wants you to be either.
So we are probably out of time here. So
okay.
I know I want to keep going, but I gotta cut it off. But I do really want to follow up sometime soon. We can do a little totally geeky bonus episode. So you're with a new shop now. So tell me a little bit more about your new team.
So Prosper Machine Tool is a small business based out of Texas. Our office is over towards Fort Worth. We are a group of we both sell and service CNC machines and metrology equipment. We have a full team of people who can work on repair, get you back up and running for all your CNCs. Tons of experience. These guys are. I am not a CNC repair guy, but these guys know their stuff like crazy. I talk to them all the time because it fascinates me because the worlds are very similar but also very different. And then there's me right now on the metrology team. We're here to help you. We have a whole sales team to help you if you have interest in OGP or material products. We also have probably 5 or 6 lines for CNC machines, lathes, mills, kind of whatever people need.
Well, how can folks find you guys?
So it's Prosper MT. That's like PROSPERMT.com.
Cool.
And we don't do a lot with small tools, hand tools, stuff like that. We do mostly large machines. So we're kind of here to help however you guys need.
Awesome. Cool. Let's see. Oh, there we go. All right. Sorry. Still trying to figure out some of the fun tools I can do on the video streaming.
Of course.
System here. And, learning while you go. That's just the best way to do it, right?
Hey, I'm pretty sure that's how we both got our qualifications, learning as we go.
Amen to that. I think that's the case for all of us. Oh, man, I feel bad for Caleb when he first started here. It's like, hey, you know anything about computer programming?
A little bit.
There's the fire. Don't burn.
Yeah. I was gonna say, that's how I learned 3D printing. That's how I learned. I bought a cheap 3D printer, spent so many hours, elbows deep in it. Now I ended up getting to a point where I was building them, and now, I just buy nicer ones now because I know they're gonna work. And I'm not home enough, but I'm here. If anybody ever has questions, you guys can reach out through Kyle if you're ever looking for some advice on metrology stuff. If you're looking for new machines or service or something like that, prospermt.com.
Awesome.
It was great to meet you, Caleb. I know this is our first time together, so
you too.
Awesome. Insights.
That's awesome. All right, well, I will go ahead and wrap her up here, but hang on for just a minute, and maybe we can talk about scheduling some time to get a little more geeky.
Sounds good.
All right, everyone. So that is it for today's episode. A little bit longer than normal, but this is kind of fun stuff. So it's fun putting this stuff together. It's fun having these conversations. And, the quality world is one of these where we're all so serious so often and probably take ourselves too seriously. So we just need to be able to have a little bit of fun and understand these things from a real world perspective. So if you enjoy what we're doing, check it out. Be sure to like, subscribe on YouTube. You can find us iTunes, Spotify, wherever. We hope to hear from you soon. Y'all take care.